get started with the panel. And so 2 of the speakers you already know because they've given the talk this morning. And then there are 2 others who will be speaking afterwards. So there's Gabrielle. She is giving the dinner talk tonight. She is at NCSA. Do you want to tell them what you do?
Sure. I'm a professor of astronomy at the University of Illinois. I'm also the Associate Director for Research and Education at the National Center for Supercomputer Applications. My background is really working on community scientific software frameworks, particularly something called the Cactus Framework, and I'm going to tell you a little bit about that while you're eating dinner tonight.
And the other speaker is Kirsten. Kirsten is going to be talking about provenance later today, and she's from Brookhaven National Lab, and she'll tell you some more about herself.
Hi, I'm the director of the Computational Science Initiative at Brookhaven National Laboratory. We are specializing in bringing computer scientists, mathematicians, and computational scientists together to enable them to use the latest technologies in their codes to do better science, more science with their systems. What I'll be talking about is provenance, as Anshu said, and well, we'll talk about that later.
Catherine's going to be managing the questions, and I'm going to be managing your questions.
And what that means, as I said, is we can talk. We have questions that might be interesting and that are follow-up from what people say, but I'm going to beat you over the head and say, but we'd rather yours. And one follow-up I wanted to make a comment on, and it was actually from the conversation about copyright and licensing before we get started, is that Mike Roux had to leave, but had a statement that he really wanted to clarify something. And I think this is a really good illustration that if you own copyright on your code, right, you own, for example, the ability to change the license on your code at any time, including change the license on your code even going to different sources, right? So you could send your code to a collaborator and have one license on it and send it to industry with another license on it. It is important to understand if your institution cares if you do that. And this, again, goes back to ask your institution about it if you have any questions. But copyright allows you that flexibility. Copyright can also have a situation where you have copyright within even the same routine, right? That somebody contributes code to you, but actually wants to retain the copyright on it. This does occasionally happen, right? With institutions, wanting to own the intellectual property of what's going on, and that's something that also does have to be managed at times. But we can also follow up more questions about licensing and copyright. So I will start. Are there any questions from the audience before I start with some of the questions that I've sort of been picking out over the past day and a half? Excellent.
So regression testing has been discussed a little bit, and one of the kinds of regression testing was with respect to performance. So it seems like, so first of all, how do you handle regression testing with respect to performance? I'm assuming one might run the particular codes on their systems and see if that changes over time, but how do you establish a baseline for what's a good performance across maybe multiple systems? For instance, maybe a system that you're running it on for the first time is not configured correctly, or there's some feature of the system that makes that code run poorly. How do you establish a baseline for what the performance of an application should be?
I love that question. One answer, very quick answer, I'll say, is that there's an intuition you'll get with your code, right? It's not going to be that intuition will be right, but you'll get a sense, right? If your code is suddenly doing something very different than what you thought it should be doing. And so it's not that history is the only way to do it, but history can have help you a lot with that in gaining some insight. And you also know basic numbers, right? You can look at the basic specs on a machine and get a general idea. My code maybe should be like, twice as fast given what they've done, right? And when things go beyond that, right, that's where you really want to start looking more closely.
How about a community code where somebody who's downloading it and they don't know what to expect?
Who've used the code, if it runs as slow for them as it does for you, because that's usually the problem, not that it's running too fast. The other thing, if you really want to dig deep and you think, okay, the code should be running faster, you've tried sort of the usual things, is done really performance modeling. And there are a number of tools out there that really help you to analyze the code and see how fast it should be running and where it's losing its performance, both in terms of not utilizing the system, but also where you have to improve the code to get to where you need to be in your performance.
Many community codes will publish performance information so that you will be able to have that as reference, right, as one starting point too.
The code that I work with, the Cactus framework, is a modular framework, and so we very much, I think, have this challenge, and that we spend a lot of time every couple of years doing intensive benchmarks and making sure that all parts of the code are running as well as expected. But when we do production runs, they're made up of a lot of different community components, and then I think it ultimately falls back more or less to intuition and experimentation on this. We have tried before. We do have regression testing, and the idea is that for each component, the person who writes it should provide a test that tests out different parts of the system. It's hard to have our developers are mainly coming from science domains. It's hard to encourage them to always do this. It's actually hard to convince people to always run the test, because they take a long time if they're trying to get on and do the science. So I think we'd be very interested to experiment with maybe more automated ways that it could at least potentially flag that there might be a problem or something unexpected. We tried to bundle it up at one point to remember results from machines that were being run on, so that we could compare and see if anything was changing in the same time that we do nightly builds and tests. That would be one way. But typically the tests don't necessarily reflect the production runs, which is where you see the problems.
So I would say two things. One, sometimes this information is already there. It's just laying in the tests. If you have a test suite or a set of tests, it's just how long they take to run. And it's there and not always just recorded. And so it's if you have a test suite that runs on several different architectures, just looking at how long different tests take to run and writing it down in some way is useful. More formally, for run planning, typically you'll have the numbers for your if you're testing your science setup, you'll have numbers for that, and those are the numbers that you're already using to do your scaling, to budget your runs, and so those are the numbers you are most interested in anyway. And so just as long as there's checks on those and you can look at them, so it's not. I guess that's maybe less formally. It's not as formal. It's not like a defined test, but you know what your timing is for your science goal, for the science runs are. The other thing I would say is that you can build them into the test suite. Some of the MESA test problems actually report whether they ran in the amount of time expected, because often the failure mode for that solver, because it's an iterative solver, the failure mode is that it just takes forever to run. It's not really that it gets the wrong answer. One of the biggest indicators is it takes longer than expected to run. That does sometimes take a little bit of work on. You have to make sure it runs on the right number of cores. It's going to run differently on different architectures, so that's not foolproof, but it can be built into the test. So.
There are, of course, tools that you can use to instrument and get the performance information out, but there are new kind of tools that are in the pipeline now that also measure the number of operations. So you just feed it to the tool and it'll come out and it'll tell you its features like arithmetic intensity, et cetera, et cetera. These can be very informative about also in terms of mapping expectation to what you're actually observing.
Are people familiar with the term, the mathematical intensity? Sort of like
I sort of defined it in one of the talks earlier.
Okay, I couldn't quite remember. Yeah. But that's really valuable, right? Because in the end, right, what really matters is whether it's fast enough to get you your answer first, right? And then can you get your answer faster? And those two, that type of information can help you answer both of those for you.
The other thing to bear in mind is that there might be a limit to how fast your code can run, at which point you should just stop doing anything to it.
And then so if you're not aware of Roofline Model, you ought to be, because it is the thing that tells you what to expect from your code and when to stop optimizing it any further. How many of you know about Roofline Model? Okay, not nearly enough people. So everybody working on supercomputers ought to know about it. It was 4 years ago, I want to say. So you search for it on Google Scholar, you'll find it. What it does is it defines, it basically makes a line which is the upper limit of what performance you can expect to see based upon the arithmetic intensity, which is the number of times you use a data item after calling it, fetching it into the cache once. And based upon that characteristic of the code, it tells you what is the maximum performance you can obtain on the code. And I think there is also a toolkit getting developed that can measure the roofline related performance for various codes as well. These are, I think some beta form of it is already in release. It comes out of Berkeley Lab.
Another question from the audience? We can also feed interact, right? We might ask one of the other ones we've got that will trigger more. One of the ones that I thought would be really valuable to talk with everybody about here on the panel was a question yesterday that I didn't like my answer to it because it's a bigger question that requires perspective. And that's, what do you do when you walk into a group and there's no software engineering, there are no good software practices, and they don't want to change, right? What kind of approach can you take in a recalcitrant group about changing practices, generally changing practices? Anybody want to start on that non-trivial problem?
If you find a group like that, you run very quickly into challenges. We just recently had a case like that where we found that there wasn't a working version of a code. They were just happy with it crashing in the end, but it got the last answers out that they wanted. So that is usually a good starting point to say, well, maybe this isn't the right way of running it. And when you dig deeper, it's usually because 2 or 3 people work on the same code. No one's doing any version control. No one's doing any testing. And so that's a good starting point for discussions to say, maybe we can do this differently. In particular, maybe if this is a group that's on the verge of giving the code out to a wider community.
I think it depends whether or not you're the person paying these people, and you can tell them what to do, but it's assumed that you're not. So I think we have at NCSA, we've started having, I think this is not I haven't seen this be an issue at all, but we do have monthly software meetings. We have a mailing list, and a lot of people come. We have talks, we have discussions. I think you show by example. So you just want to have the developers and the people in the field be able to pick up best practices by seeing them working for others, by being in environments where they're discussed and shown, and they can see the outcomes and what they lead to. It turned out when we had the first of these meetings that not everybody in the center was using source code repositories, for example, and then they hadn't actually sort of heard about how you use them, and that there were actually people that were sort of struggling to still develop code by emailing it to each other. And I think that very quickly, from just having a couple of these meetings, we now have a lot more code that's in source code repositories and starting to move to having shared practices that then become more efficient, and there becomes more experience. And then people coming into that environment just automatically pick up the habits. I mean, I think that's always been my difficulty. I've moved places a few times, is building up a critical mass so that you have enough people working with good practices that can help to just educate by example people that are coming into a team.
So this question is sort of like about evangelism, right? And so I think you have to borrow practices from the evangelists. Be persistent and be passionate, right? Point out the benefits of good software engineering practices and don't stop, just keep on it. You have to be persistent. And there's now, I think, these days, a lot of resources that you can point to that demonstrate very clearly the benefits of good software engineering practices. And there's also much more in the way of tutorials and useful ways to get people started very quickly in using good practices in their software development. And that wasn't true, I think, a few years ago, not as true as it is today. And so I think the barrier to doing it is much lower, and you just keep pointing that out. And you do it yourself, and you demonstrate your passion for doing it, and you evangelize.
So one thing I would say for Mesa is that this is usually given to a new, if someone uses Mesa for something, it's termed for them in their own self-interest, which is if you can provide a test for the thing you're doing, it's much more likely that it will still work in the next version or going forward. And so really it's a self-interest thing that, that doesn't apply to situations where the code already exists and there isn't already a test suite in place. But certainly for users coming on, once you have some infrastructure, it really is a self-interest thing. And so that hopefully is motivating. Usually it's, you know, the first time people don't do it, and then the second time people do. It's, you know, got to learn by trying.
So there is one thing that is also important is to never give it an appearance of, you know, not having any flexibility when you're trying to sell these ideas to people, because as soon as you start to sound too much like an evangelical, you will fail also. So let me give a further twist to this problem. So here you have a group that doesn't do software engineering practices, and you can clearly point out to them that, look, these are the ways in which you can do it better. What do you do with groups that think they do software? And they think they do adequate amount of software practices, but they don't really. Because they're even less open to suggestions. And that's the problem I encountered, and I did not make any headway in there.
So I had the privilege to work for the National Science Foundation, help run the software program. So we addressed this by writing it into the solicitation that people had to describe before we would give them a grant. They had to describe their software engineering process. And then it's up to the feedback from the peer review and other program officers, but try to address it by explicitly making it clear that the funding might be dependent on having good software engineering practices. And
which also means that the reviewers ought to point out that what you think is a good software process isn't really one.
yeah.
Yes.
I have to say, I think the last grant I just got, we actually had the program officer came back and we had to write some more material on our software engineering processes to get the funding. So that worked.
One of the other things, if you are in that scenario, some are more difficult than others, but in the nicest way possible, right? Because it goes back to you can be an evangelist that gets sort of knocked out of the court, or you can sort of, you know, bring it up in a useful way, and you have to measure the dynamics of whatever group you're in. But you can point out when something does fail because of process, right? And you can do that in a nice way. There's a lot of really easy ways to do it hard and terribly, right? But you know, do sort of your best practice in terms of, you know, good dynamics there. But pointing out where there is an issue can be really effective.
I mean, maybe one more point, since at the university we also have an opportunity to teach the students and train them. I think many people here are graduate students and postdocs, perhaps going on to be teachers. And I think that we don't teach students enough about software practices. We assume that they pick this somehow up on the fringes. We don't, you know, we teach people basic math and basic English, but we don't teach them basic software. So we've been working a lot with the software carpentry group at NCSA, trying to introduce a lot of training, trying to encourage departments to work with us to try and encourage their students to come along. And really think that at one point then, if this basic training, if it's part of the curricula and we can make sure that students in the relevant disciplines are having this training, maybe we won't see this problem, because it'll be the same as calculus and people will just come along with the basic training and the ideas of what is important.
So I mean, I think if one group thinks that the testing is sufficient and another group thinks that it's not, usually there's some communication that can happen, right? I mean, clearly they perceive, you know, what sufficient means is different. They may perceive what testing means is different, and so if you can, you know, converge their definitions, you know, it can go a long way to you know, at least if each side can understand where the other's coming from, you can find something in between that's productive. Because I mean, you know, especially if a scientist sees it as an annoyance, you know, they're more likely to just say, no, it's fine, just out of, you know, self-preservation. They're just trying to get on with what they think is their priority, and so, but understanding, I think, can go a long way.
One quick thing I'll add to it. We've mentioned this, but I'll make it really clear that today is incredibly different than what we were looking at 5 years ago in terms of tools to help with engineering practices. It is incredibly different, and if you compare to 10 years ago, it is almost incomparable. It is like black and white. And while some tools that might be ubiquitous today might have been around 5 years ago, they weren't ubiquitous, right? They were starting. And so that's another thing that's valuable to keep in mind, depending on where you are in your career and how long you've been doing this. Chances are you might be interacting with somebody who's been doing it for 10 or 20 years. And 20 years ago, too, like setting up a repository was not impossible. You know, I did it many, many times, but it certainly wasn't go into a web page, right? You know, and upload some code. And so that's something that really impacts people's perception about this. Absolutely impacts it, where they think it's onerous and a pain to do, because it was really recently, until really recently. I will ask any questions again yet from the audience? The second one? Yeah. This does not have to be one way.
So in science, a lot of the metrics that are used are based on paper count at the moment, or on the question of how good is the paper you published in. Do we need something like these indices, regardless of how well they're seen in the community, also for software? Especially if one is not mainly in the computer science part of the field, but more in like application fields where HPC is just a necessity, not the reason to do research.
One thing I would say is yes. There's a lot of reasons that motivate it too, and it's not just because of making sure sort of that you get the get credit back to it, right? So whether the current model, right, how do you reference using a code for the most part is that somebody publishes a code paper at some point, right? And that code paper is what you cite if you're using a code for reference. Even that model has a lot of challenges, right? Because who comes and goes on the code changes, right? So if you're a primary developer on a code, this might have happened to people, but you come a year late, right? You're not on that paper anymore and you don't get those citations. But also, you want to make it easy for people to cite your code, right? You want to make it easy for people to be able to say, I use this code to do my work. And sometimes you're dealing with limitations in the paper, right? And so there are alternative ways being discussed, right? About how you can put, sort of a unique identifier, right? To sort of give proper credit to a code, or there's other ways this is being considered too, having to do with other things within HPC, but there's a lot of value to that, right? Because then you get the ability to bring people in and get their credit early on. You make it easier to do the acknowledgement of the code, so it doesn't have to take up sort of sometimes that limited space you have when you're writing a letter and you have only so much physical space you can use on the paper. But there needs to be a better way to do it, and a more ubiquitous way of doing it, in a way that's assumed that if you're writing a code doing a simulation that you do reference something somehow. Because it's even that, I don't think we're not even at that point yet, where you always cite the code that you're using.
And I think that's probably a good point to expound on. If you think about it, one of the core principles of science is reproducibility, that others can see what you've done and can follow that. And without any way of citing the code, and not just the general name of the code you've run, but which version, what exactly have you done, it's very difficult for others to reproduce your results. Or if you can't show what it was that you used, for you to defend the work and the results that you produced with it. And that is not, even if you're just using a code to produce your science, it becomes suddenly important that you can show how you created your science results and that your results are valid because you used the right methods of creating them.
Yeah, this is a really tricky thing, right? And I think this is where tools like GitHub and GitLab are going to have some impact, because there you can get metrics. You can see who's made the commits, right? And who's forked the code, how many people are following the code. You can get some alt metrics on a code. And like Catherine mentioned, we're moving towards having things like DOIs for codes where you can cite them in a paper. And so it's a tricky thing, but I think people are working on solutions to it. And I think you can point to these metrics with tools these days that are helpful in at least saying, look at the big contribution I made to this code that has had an impact on so many different users.
I think there's a group in Force 11 that's looking specifically at software citation that Dan Katz and Arthur Smith are chairing, I think. Arthur Smith, who's at GitHub, gave a colloquia a couple of weeks ago at NCSA, which will be online very soon. And he basically was talking about this for about an hour, about the challenges and possible solutions for citing. I think there's a lot of problems. I think we use citation to measure many different things, and so thinking about what kind of credit people get. But people are talking about this, about the challenges. I think there are also things that we have another workshop series, WISPy meetings, working towards sustainable software. I can't remember what the last S's and P's and E's mean. But that's also, we have a working group there that's also been talking about what could be mechanisms that we could use right away to start citing software. I think that's something that is even a challenge when we think about how do we even put a thing on our webpage for software to tell people what they would cite when we want them to cite it. And right now that means writing a paper and keeping a paper up to date. The authors, it means that in our case for Cactus, we have authors from 20 years ago that get all the citations. It's hard to add new authors and so on. So there's a lot of challenges, but I think that if people just started trying to do this more, all these things would get ironed out. And I think that there are ways that when you're thinking about how to express this on your own resume, I think people should start going ahead and making the case for the software, making sure that they include software in their resume and tell their own story, because you can explain it yourself, how many lines of code you've contributed, how successful those have been, and to make sure that it's included, make sure that if you're hiring people or on a promotion committee that you're including software as in a right way, and trying to change this attitude of only looking at publication citations.
So I want to argue that those of you who are in the academic world, the onus is up on you also to change the culture in your own respective departments in terms of what measures. Even if you can't do it today, soon you will be able to. And at that point in time, this is no longer an excuse that you can give, that the academic world looks at it differently, because you will be the ones making decisions.
Yeah, and this is something at our new department of computational math, science, and engineering at MSU. This is something we're very explicit about, is that software matters. We consider it a real intellectual and academic contribution that matters. And that's explicit in sort of the foundation of our new department.
So my question especially concerns the science and the claims done by the closed codes. So you use it in the closed groups. So my understanding is that in most of the groups, they provide a partial solution to this, that they provide a basic algorithm and the major approximation that they make to solve the same system of equations that other people haven't yet achieved to solve it, or they have different codes. So that I think is like a one first step that we can say. But sometimes in the same paper or in different paper, they give different solutions, or they say that we did this approximation and this changes even in the same paper. Like if you read the abstract, it will change in the conclusion or something like that. But in terms of the major claims, something like gravitational waveform from the core collapse supernova, something like that. I mean, when the science claim matters, how, and this might be a little bit personal question, how much we should grill the authors of the papers that your code is closed, and you have provided some basic algorithm, but what are the fine-tuning parameters that you are using in your codes? And how much we should ask, like we should just keep on asking until the last point that we have all the essential elements? I mean, they're not going to tell us, right?
That is an excellent question. And if when I talk later on, that's exactly what I'm going to talk about.
I think for astrophysics, I don't know the solution to this kind of issue, but really it's a question of practicing or demonstrating good practice, and then trying to move it or encourage more of the community to have good practice. Typically, in my experience, what gets in the journal and what happens in the journals between, say, the referee and the authors has a lot to do with what is the common practice in the field. And so if it's common practice in the field to just present a simulation that the authors were able to do with kind of minimal ancillary information, if that's general practice in the field, that's what's going to happen. Because you might have a referee that steps up and says you have to put more in, but it's hard to do that if there's 3 other papers that are on exactly the same subject that didn't do that. It's not fair to those authors. And so the onus kind of has to be on the other side, which is that we have to, as authors, as scientists, make sure our papers have all that, show the best practice, so that, eventually the industry practice or the academic practice becomes closer to what we think of as the ideal, where things are actually reproducible. You give a code version. Ideally, I'll just give the example of the MESA papers. The MESA instrument papers, so there's been 3 of them so far. So they're the sort of the core MESA papers. Every figure can be generated. The files to generate every figure are available from the MESA websites. And that's the way that, so the MESA sort of core team has taken the tack of kind of trying to set the example of making sure that everything is reproducible, that you can, if anything in that paper, you can just download the appropriate version of MESA, download the parameter files, and just run it and reproduce exactly what's in the paper. And so a lot of it is just pushing that industry practice forward, and so that it becomes more common and more expected. So the referee can just say, "Oh, you should be doing this. Everybody else does this," and I think that'll help.
Why should it not be a simple editorial reject, a policy of the journal?
Because it's not standard practice. It's not.
Yeah, but it's not individual reviewers can't start it, but a journal can.
And some have. Some journals have started trying to do this, but they have to do it carefully too, right? There has to be a gradual transition. Yeah, or they'll fold was a comment that was made. Really, seriously, right? They won't get people submitting to them.
There is also the America Recompetes Act, which points out that anyone who has funding from the US government for their research actually has now the duty to put auxiliary information with their publications that make it, that is good enough to reproduce the results. And so I think that will help to change the attitude generally. Now, what that is, as you just said, it depends on the different communities, how much you have to provide, but that is a requirement for everyone now.
So I have lots of thoughts on this. So I've been the person that's barked up that tree and said, why don't you make your code open? And it goes nowhere, right? And then I've been the referee that Dean just described, and I just insist. And I insist on them providing more information. Because I've refereed papers that cite non-existent code papers, right? There is literally not a code paper describing, what they're actually doing. They describe it in vague and terse terms, and there's just no paper for them to actually point to that says this is our code, and this is how we're doing the various approximations. And so I'm that referee that just keeps badgering them to include enough information nominally so that we have an idea of what's going on. That's not to say that they're doing it right, because we can't see the code. So, it's impossible to insist that people make their code open source unless it's enforced from above. But as Catherine said, that's risky for a journal to do. But I think increasingly the funding agencies are enforcing this. They're starting to encourage this from above, and that will help a lot, because it's only going to happen in that direction, I think.
I'd echo all of that. I would encourage you, if you want to do this, to contact the authors, contact the journal, contact a funding agency if the software is being supported by a funding agency, and pursue that. I think there's lots of reasons, as have been mentioned, why we want to have the code there for reproducibility, also for education. I feel when I was learning astrophysics, I pored over standard papers in the field, tried to reproduce calculations, more theoretical at that point. I think we have an opportunity as well to use the people learning the field to do some of the reproducibility, and if there could be some mechanism by which we could sort of tag field papers, as you know, potentially authors could say, yes, these are reproducible, and that would help. You know, then they would be the papers that the students would be reading. They would get cited more, and that would be an incentive for people to make their work reproduced. And in the same way, there might be a way to be able to tag the papers that have been reproduced, which would provide more confidence in the field. Would also be able to highlight errors, because we know that, you know, there's a lot of errors to catch in places. And so I think there's a way that we could put a number of things together in making the codes more available, and having, I think there are a number of people that actually would like their work to be reproduced, and would like a better mechanism to get it out there, make it available. And this is all changing. I think, again, this is one of the things that 5 years down the road we'll be wondering about the time when computational papers were not reproducible. And
So I'm obviously not on this panel, but I do make a living out of modernizing old code, which is frequently closed source. And a couple things have been said here about changing the culture of a group or changing a mentality. And this is something I run into frequently in my day job. And I just wanted to point out that I found the best way to convince people to use good software modernization practice, or maybe that their code should be open source, is look for the common element between yourself and the group you're working with, which is almost always performance. If you can find real quantifiable benefits to making that change in their culture, they're likely to do it. So if I can go to an engineer and I can show him, if you write your code using well-defined modules with intent on your parameters, and that gives the compiler an optimization opportunity that makes it 10% faster, he'll do it. But if I go to him and say, you know, code should be modularized, he's not going to do it. So you should show him data, reasons to actually change. And then the same thing with open source. Go to someone and say, your code could be open source, and it'll increase your visibility in this community, and show him how much. But if you just go and say, you know, code should be open source, they're not going to listen to you. That's just a little. That's just my input here.
Thank you.
Hi. So you were talking about making the code public and open so that other people can use it and reproduce it. So when we write a code and we make it open, eventually people come up with a bunch of issues and bunch of problems. And as a graduate student, I have to get my PhD done. So how much would it be to actually have maintain the code? My time should, how much time should I spend to maintain the code and go for my PhD? There should be some balance, and I just want to know the thoughts about that.
So I think there's a difference between making your code open so somebody can check and reproduce your results, and committing to supporting 200 users writing to you daily. And so I think that there's sort of best practices for how you'd make your code open. And I'm sure you would, you wouldn't think of writing a paper where you didn't check your theorems and analytics, right? So the same, you make a balance for how carefully you check your math. I think you have the same thing, that we haven't yet figured out what the right setting is for how tidy your software is. But I think there's a difference between making your code open and having something that you're confident people will be able to understand what you did and have trust in your results, and supporting a community of users.
Usually for the bigger group who has a lot of funding, they usually put a system administrator or somebody who actually maintains the code. But for a smaller group to actually put out the code, it's quite difficult to hire somebody who just maintains the code. And so either he doesn't make it public, or it's just...
Again, I think that you can make any code public. You put it onto a open source code repository, and that takes about 5 minutes to put it there, or you put it on some other place. I think it's the question you're asking is whether the code is of a standard that you would want other people to be looking through it, and that probably comes back to the confidence and trust in the results from my point of view.
Chime in into this one, and this goes back to one of the points I made during the time that I was describing how you design your software process. And your software process you design based upon understanding the scope of your project. If you are a small group, you are not likely to have produced a very complex code, for the simple reason that you don't have the resources to produce that kind of a complex code. And therefore, your software process will be commensurately lightweight. And there's no reason why you should not be able to maintain it in that lightweight fashion. Because you're not maintaining the code not just for the use of external people, it is also for making your own life easier down the line. So you don't have to, for example, if you don't have to have the complexity of running an automated test suite, it still does not absolve you from having a set of tests that you run every time you make a change to the code that is substantive to make sure that it is still running. Because otherwise, how are you going to have confidence in your own software that it is still doing the right thing?
I would come back to what Catherine said before. There are so many tools out there that I don't think it's a large burden. It will actually save you time. So even when I started doing software development 30 years ago or so, I would use a source code control system just for my own code, if nothing else, so I know what I've done. And if I've done something wrong, which happened regularly, I could go back and change it and make it right and see what I did to break the code. Being able to do that and do that easily just saved me days, if not weeks, of work. So it was just for my own benefit, if nothing else. Systems like BuildBot also that check if there's even a small group of people that develop the same code, that check in, and you just run it automatically overnight to see if anything broke the code. It doesn't cost you any time. It takes a little time to set it up, but not much. And then it does it all for you. All you need to do is to fix the problems that you put into the code, but it's better to do that than produce results that are incorrect and you have to withdraw a science paper.
One thing also to consider is that communicate, right, make it clear. This is part maybe of Nathan's talk, right, that I didn't do complete justice to. Make it clear what you are doing in the process of your code, right? So in terms of testing, make that clear to anyone who might take it. But you can also make clear, right, to people, and you'll get the occasional person who's just not understanding anything, right? You can make it clear that we can support this kind of bug, bug submissions. We can't support, can you implement this great new physics? Just communicate that, right? Just make it clear. And I think most people would understand that. And that process alone, right, is valuable. And then beyond that, right, if you do start with your code getting a lot of people downloading, a lot of people asking questions, there's a great concept of community support, right? And this happens with a lot of codes. What that means is that whether it's a forum or whatever, right, a mailing list, but some way that people actually start self-supporting, right? And so, you, for example, don't have to answer a question, but user X answers user Y's question. And this is true, this happens, and this is part of cultivating and communicating with your your sub-community and your science community and your user community. But just make it clear. If you can't answer, particular questions, just let them know. I'm trying to graduate, and I think most people would get that one.
Two different things. There's a different thing between publishing the code for a paper so that people can see what you've done and check reproducibility and doing any kind of. And it was only just arrived, so I don't know what you've been encouraging people to do open source or open. But I think you can keep your own code private, and you don't necessarily want to be. That's the choice as to whether you want to be doing all your bug fixes out in the open. But I think talking, I think I would encourage you to do that in an open way. But I think that I think your question is about whether you make your code available for the publications you're making. If that's the case, then I think looking at making sure that the code is written in a standard library of standard language, so that it has a very good chance of compiling in the future. Because the questions that you would be asked is when somebody wants to check your results in 10 years' time and downloads the code and tries to compile it and finds it was written in some kind of weird, extension language or something like that. But they're going to want to compile it and run it, and they're going to be asking questions in the same way that if they found a mistake in your paper, they would be contacting you to ask you questions about how did you get from this line to this line. So I'm not quite sure which question you're asking about whether you should be doing you should be providing as part of your graduate studies an open code base and supporting it. Sorry?
Both, should I make it public and how should we maintain it?
But I think I think really the right point though, right? That your code doesn't have to be open, right? And open does not mean that it is supported, and open does not mean that it's a community code, right? All of these things, right? They're not equivalence classes. They're not. And you define through communication with your community.
But I will still emphasize, for your own sanity, you should still have whatever process makes sense to you. But you should have a process, because in the end, whatever little investment you make in getting that in place at first is going to give returns several times over the course of your PhD.
I have one question that sort of was percolating through some questions that I saw over it was buried in some questions that people were asking over the course of the past day and a half, and there's no way we'll answer it in 5 minutes. And I apologize, you can throw tomatoes at me, but. So I think maybe the question that I was hearing behind some questions was, what does performance portability mean to all of you? And do you really think it's feasible? And we're laughing a little bit because I think many of us have had a lot of these conversations in the past 18 months, and they're a good conversation, but there's been a lot of them.
Go see the ideas, how to, and what is website. It defines and it gives you some possible ways. That's the state of the art.
But do you think it's possible?
Yes. At least for the kinds of problems that I'm aware of, I laid out a software architecture that would make it possible. Possible? Yes. Probable? I'm not too sure, because I haven't been able to convince any funding agency to give me money to do it yet.
So I think it is a very challenging question, in particular with quite a variety of architectures out there now that are quite different from each other. And so good performance or decent performance on all systems, I think, is possible if you follow good software engineering practices. The highest performance on all of them is probably much more challenging to achieve, and that's a research question, to be perfectly honest, to see how you can do that. And today's approach for most people to achieve the highest performance is really hand coding, hand optimizing the code. Clearly that's not sustainable if you have different architectures and a large code base. And so the research that we currently do, for example, in the national labs and in other places as well, is to look at what can you do to make this process easier. Using, for example, compiler directives or other things to put the last bits in that will allow you to optimize your code to a much higher level on different architectures. But unfortunately, there's no silver bullet yet out there.
I would argue that even on current architectures, if you're looking at a real multi-component complex code, you do not achieve highest performance on a single platform. You're still looking for acceptable performance on multiple platforms, because these codes almost never decide in favor of a high degree of hand-coded code, because that just takes away the portability.
I think that's a question of the community. We deal a lot with communities that really bring hand code and hand optimize their code to get the highest portability, highest performance on the different systems, because it's important to them. They don't get that performance, they don't have enough science that they can get out of them.
One of the things that I sort of see as necessary is directly related to what you're commenting on, is that if we ever want to see a point where on really, really two different systems, really big systems, you are seeing consistent performance, a well software engineered code that will do that is a different code than what we know of as a scientific code today. I don't mean that it's like unattainable, but it won't be engineered or architected like we do it today, right? People have ways of writing their code today. They have ways of thinking about their data structures and their use of libraries and their process. And I think if you want to have a performant code across really different machines in 12 years, you're talking about a code might take longer than 12 years to write because we don't have all of the mechanisms, but it'll also look super different. It will have a different relationship with it as a scientist, I think.
So I think as well, it's not the approach to this also has to include looking back at the base physical problem, scientific problem that you want to solve. So in my community, we've been mainly based on using finite difference stencils for solving very complicated partial differential equations. And the community is now looking at discontinuous Galerkin methods. And part of that is because they should scale a lot better because the stencil is much smaller. And so you can split them up along these much smaller cores. But that's something that you can't just do a performance analysis and redo your code. So that's an algorithm choice. I mean, it might be that we really want to think much more about the algorithms that we're using for different platforms, and also to think we also try and put in the code base as much dynamical decisions as possible, because it might be that your a particular, as you mentioned, different components are going to perform in different ways, and it might be that the component that is actually taken up all the time actually really isn't that important, and we don't really care about it. So we could just turn it off while we're running, and we could do that analysis later on, maybe from output data. So having higher level interfaces, so you're getting more to understand from the scientists what their priorities are and what they actually need to do, I think is also part of the question that part of the solution rather.
The only thing I would say is that I sometimes have the concern that oftentimes when a scientist is doing development of say an algorithm or methods, that's what the first time that's done, that's a prototype. I think often the prototype ends up being moved into production, and you really expecting that then to fall into some framework that'll work better or worse on some machine is really kind of unrealistic. You really have to, a prototype is a prototype. And using a prototype in production is nice, but it is what it is. And so if there has to be more investment to take a prototype and move it into production on a particular type of architecture or some meta architecture that will work on more than one. And so that's kind of like a whole separate step that requires investment of time and money.
Yeah, what we like to say is never let optimization get in the way of results, right? And I think, there's sometimes, performance portability, you can be good enough, right? If I'm getting good enough performance on two different large-scale machines, maybe it's not optimal for either one of them. If it's 80% of what I might expect for optimal on either one of them, good enough. Don't let optimization get in the way of the results. But yeah, and going back to what Catherine said, if you're getting very comparably good performance for the same code on two different large-scale machines, it probably means that code's really slow and not performing very well on either machine.
Yes.
But it is a tough thing. Yeah.
But in my experience, and there are codes where people have full different modules that work on different machines because they had one particular piece of code that was the performance critical part of the code, and they could have two different implementations of that exist. In codes that I have worked with, be it Acme, be it Flash, that's just not feasible because there's so many different components that plays 20%, 10%, 30%. You cannot have many different existing versions of these codes. And what we found was that in almost all of the instances, a greater degree of performance improvement was found by re-examining your approximations and re-examining your algorithms and data structures. And once you applied them, they worked across the board. So I will still tend to disagree with you on platform-specific optimizations, because I think that is the easy way and the cheap way out. That doesn't really pick up all of the possibilities of good software that are there.
What I would say, though, is that you have, like, for example, today, some of the groups we work with that do really low-level optimization, they try to do this with an engineering approach, right? So they try to effectively just write their own libraries is what they do, right? They basically, there's one community that has, it's probably 3 or 4 tiers, right, of library dependencies that start, with talking to the lowest level API that they can possibly talk to for the network layer, for example, because latency matters everything to them. They need the lowest latency they can possibly get. And so they try to execute good software engineering practices, but it is really expensive in the sense that they do have whole teams of people who are devoted to basically rewriting those libraries when they want to move on to a new machine. And so for them, it's really crucial, it's really necessary, but they try to do it well. The other thing that's related to what you're saying, Anshu, is that with applications today, with most science applications today, if you go through an optimization process to make your code run really well on a machine, like you think about your data structures and optimizing your data structures, I'm not sure yet, I'm sure there will be an example, but I have not seen an exception where that process of improving your code for one machine doesn't actually just result in a better code. And you end up with a code that runs better on 2 machines because all you've done is actually make your code be more effective and perhaps better able to use the memory hierarchy or the, the cache system or, the GPU memory or whatever it is, right? You've made, for the most part, all of these optimizations are data movement related. You've made your data easier to move around. And so today, that is absolutely true today because we're dealing with a whole giant family of science applications that have been written for the past 25 years, 30 years of machines, right? And so just that process of thinking about, sort of our more heterogeneous world today is actually a huge boon.